Today we're going to talk about starting over. Second order linear homogeneous differential equations with constant coefficients, and it's going to be of this form. So what we're going to assume is that the solutions is going to be of the form e to some power. We've seen exponential functions a lot already, and it seems like that would kind of make sense that the solution would look like this. So for now, we're just going to assume that it looks like this, and then we're going to go ahead and try to solve for it generically, symbolically. And so if this is a solution, then we should be able to just take derivatives and put it in and then solve for whatever we need to solve for. It looks like we might need to solve for m. So let's do that. So we need y prime and y double prime. So it's m e to the mx and m squared e to the mx are your prime and double primes. And then we'll put it into this equation. So we have a times m squared e to the mx plus b times m e to the mx plus c times e to the mx is equal to 0. So if we factor things out, then the m that we were trying to solve for looks like it forms an equation or an expression with the m. And we could take the mx out because we could divide it. We know that that's never going to be equal to 0, so that's not going to be an issue dividing that out. So we're really just looking at this and then finding m values. Now, from your studies with quadratic equations, we know that there's 3 cases for this. I hope so. So quadratic formula, right? And then the thing under the square root, right? So if the thing under the square root is a positive number, you're going to have 2 distinct solutions. If the thing inside of the square root is 0, you're going to have 1 real solution with multiplicity 2. And if the thing under the square root is negative, you're going to have yeah. If the thing under square root is 0, then you have 1 solution. No. No. Okay, so 3 cases. If m has 2 distinct solutions, then we have m1 and m2 that are not the same. So then your solutions are y1 equals e to the m1 times x and y2 e to the m1 m2 times x. Right? So let's do an example for this case. Y double prime, let's see. I'm going to try to do some factoring and stuff in my head. Oh, that's not going to work very well. Minus y prime plus, no, minus 2y. Is that factor? 1 and 2? Or negative 2 and positive 1? Okay. Okay, so let's assume what we're going to assume here. Let y equal e to the mx be a solution, a form of the solution. So we have y prime is equal to m e to the mx. We already did this, right? M squared e to the mx. And so we have m squared e to the mx minus m e to the mx minus 2 e to the mx equals 0. And factor out the e to the mx. M squared minus m minus 2 is equal to 0. So for the first couple of times you do this problem, I encourage you to go through these steps. Later on, it'll be clear that there's a couple of steps here that we don't need to do all the time because of the type of, this is a specialized type of differential equation. Same thing is going to happen depending on your 3 different cases. So if we're solving for m here, and if we factor this, we can get our solutions, right? M minus 2, m plus 1 equals 0. And so m is equal to 2, m is equal to negative 1. So these are your solutions, or these are the powers to your solutions. So then your solutions, y1 is equal to e to the, it doesn't matter which one goes first. I'll put the negative 1 first. And y2 is equal to e to the 2x. Now you could check this. You should check this. Should I check it? I'll leave it up to the reader to check this, make sure it's correct. So I'll check it. So let's check. Y1 equals e to the negative x. Y2 equals negative e to the negative x. Y1 prime. Y1 double prime equals negative negative is a positive e to the negative x. Put that into your equation. You have e to the negative x minus negative e to the negative x minus 2e to the negative x. So this is 2e to the negative x minus 2e to the negative x. So that checks out. Ooh, I'm a little bit past my sheet here. So we'll check the second one. We need y2 prime is 2e to the 2x. Y2 double prime is 4e to the 2x. So what do we have? We have 4e to the 2x minus 2e to the 2x minus 2 times e to the 2x equals 0. So that works. So those two functions work for us, and we know that if we have a solution to a differential equation, then the solution is unique, and we know that it exists because we found it. And so your general solution with constants, yeah. So a linear combination of these two, and then you're done. That was easy. So that's the first case, when you have two real roots, two distinct real roots. Yeah, but let's first check the one where you get only one real root, because that could happen. So yeah. I have a feeling we should. Are we going to go over quadratic equations? So m equals b negative b plus or minus the square root of b squared minus 4ac divided by 2a. And so everything really hinges on what's under a square root, right? If the thing under a square root is positive, then you have negative b plus and minus something there divided by 2. So the plus and minus gives the two different roots. So case 1, b squared minus 4ac is bigger than 0. We get two real roots. That's the case that we just did. Case 2, it's possible that b squared minus 4ac is equal to 0. And if it's equal to 0, what do you get? You get negative b plus or minus nothing divided by 2a. So only one real root. And in case 3, by the way, b squared minus 4ac is called the discriminant. It's an important part of the quadratic formula because this is really what decides which case you're in. You don't have to look at the whole thing. You just need to figure out what's happening under the square root to decide, oh, it's one of these three cases. So it's called the discriminant because of that. And in this case, we have no real roots. What happens is that the thing under a square root is negative. So the thing under a square root is negative introduces the imaginary number. And the imaginary number will yield complex roots. Now, wait a minute. These roots are called conjugates because there's a real part and an imaginary part. And the two of these complex numbers have the same real part and have the same imaginary part. And the only difference is that one's a plus and one's a minus. So when you put it into this quadratic formula, you're going to get something in the square root that has a negative number, and so it comes out as an imaginary number, and you have negative b plus that imaginary number over 2a and negative b minus that imaginary number over 2a, and it's the same thing, and so it's called complex conjugates. Okay, so we are going to touch a little bit on some complex number theory. And we do have a complex analysis study group if you want to dive more into complex numbers. Tuesdays and Thursdays, 11 to 11:15 to 12. All right, so case one is done. If you are doing these problems and you run into a case where you have two distinct real roots, this is what's going to happen. This is going to be your result. And then that's done. Okay? Let's take a look at case two. Next page. So one real root. Let's just jump into an example because we know the general setup already, right? E equal E mx. So let's see, y double prime plus 2y prime plus 1 equals 0. Hopefully that'll yield our one real root. So we're going to assume that y equals e to the mx. What is your solution? So we need the first and second derivatives. And then we'll put it into this equation, the differential equation. We're going to get m squared e to the mx plus 2 m e to the mx plus, oops, this is y, not 1. This is y. So this y is just e to the mx. And then we factor out an e to the mx, m squared plus 2m plus 1 equals 0. So you get the picture here of the process and the things that keep coming out to be the same thing. So we'll set this equal to 0. We got m plus 1 squared equal to 0. M is equal to negative 1 is your solution. That's multiplicity 2. So that means your solution must be e to the negative x. We should check if that works. We'll check it. We need a couple of derivatives, y1 prime and y1 double prime. Negative e to negative x, positive e to negative x. So we have e to the negative x positive plus 2 times negative e to the negative x plus e to the negative x. That's equal to 0. So we're done. Y1 equals e to the negative x. Is that your answer? Well, the question is find the whole solution, find the general solution. C, we'll put a C in there. Now we done? No. Why? This is a second order differential equation. We're going to need a second solution. How do you find a second solution when you already have one solution? Reduction of order. Is this the very same problem? Okay. All right, so we would go ahead and use the reduction of order formula. We're not going to do that. So your second solution is this. Why? because somebody did the reduction of order formula. You should try it in your own time. But we should make sure that this works, right? So we'll check to make sure that y2 equals x e to the minus x works. Okay, so this derivative isn't so easy anymore because we have to use product rule. Y2 prime derivative of the first times the second plus the first times the derivative of the second. So the plus becomes a minus. And then we need to take the derivative again, y2 double prime. So it's just the first one. And now we need to take the product rule, which is going to be the same thing, right? Because it's x e to the x again. Except there's a negative in front, so we'll deal with that in a minute. So we want to simplify this. We got negative e to the negative x minus e to the negative x. That's negative 2e to the negative x. And negative, so that's a positive x e to the negative x. So our y double prime is going to be this. Simplify it because we're going to put it back into the original differential equation. So let's put it back into the original differential equation. We got y double prime. That's minus 2 e to the x, e to the negative x, plus x e to the negative x. That's y double prime. We have 2 times y prime. Y prime is e to the negative x minus x e to the negative x, plus y, which is x e to the negative x. So let's see. The ones with the x, there's a 2 negative, and there's a positive 1, so that cancels. And then the other terms, there's a negative 2 here, there's a positive 2, so this is equal to 0. So it does work. We found our second solution. So our general solution is going to be C1 e to the negative x plus C2 x e to the negative x. Done. Okay. All right. Ready for the third case? First one was piece of cake, right? Second one, it got a little harder. So, third case, complex numbers. Why don't we do an introduction to complex numbers? Complex numbers, meet my class. Class? You guys know what complex numbers are? So a complex number is a number of the form, they call it, instead of an R with a vertical line to be all the real numbers, they use a C with a vertical line. Set of all complex numbers is going to be A plus BI, where A and B are real numbers, and I equals that imaginary number we call imaginary number, square root of -1. And in some physics stuff, they sometimes use J because I is like circuit or whatever, current. It's confusion. In any case, this is your typical complex numbers, typical type of complex numbers. What else do you need to know? You need to know that, not that you need to know, but it would be nice to know that A plus BI and A minus BI are complex conjugates of each other. We could take a look at graphing them and stuff like that, but we'll skip over that. And so we're going to be dealing with complex numbers with exponential functions involved. So we should probably know what e to the I theta is going to equal to. So according to Euler, you can write this as cosine theta plus I sine theta. Now there's all kinds of neat activities we can do around this. We can expand series to do this. We can graph this on a complex plane to do this. We could do a lot of fun things, but just take it for what it is and move on. We don't have time. Well, why don't I do this? I'll make a video. You guys can watch it if you want. And then I'd be really happy. So if you're really interested, we could do one of those. Oh, wow. You can just replace it with X. Doesn't matter. I just went angle because of the trig. I also didn't want to call it X either. All right. Anyways, I'm really refraining hard from doing all kinds of fun stuff here because I really want to. I'm being dead serious. I would go off on like a 20-minute tangent, and by that time we don't have any time for the last example. Now that's an inside joke. What? All right. So this is all you really need to know about complex numbers at this point. And we'll do case 3. So if you have complex conjugates for your solutions for that thing, then you have a scenario where you need to insert the complex number, the I in there. Okay, so let's just jump straight to an example. So let's take a look at this as an example. We got y double prime plus 9y is equal to 0. And so we're going to assume that your solution is y equals e to the mx. And so y prime is equal to me to the mx, and y double prime is equal to m squared e to the mx. And then we'll put that in. We got m squared e to the mx plus 9. There's no prime here, so we don't need to worry about that. We got factor out, and then what we're left here is the m squared plus 9. And if we set that equal to 0, we can bring the 9 over to the other side. We get -9. We'll take the square root. We get a square root with a negative inside, the 9 comes out as a 3, the negative 1 comes out as an I, and so we have plus and minus 3I. A is 0 in this case. You should think about what happens when A is not equal to 0. You'll think about it. So, this is what we have, which means our solution is equal to e to the negative 3I and e to the positive 3I. Well, we did our stuff with real numbers. We should expect our solutions to have real numbers, and in this case, we don't. Oh, X, thank you. Oh, by the way, 3I is just a constant. I is just a constant. Let's remember that for a few steps from now. So anyways, we want to change this or turn this back into real numbers somehow, or a function of real value without the i's. So let's take one of these solutions. Let's take the second one because it's positive. Doesn't really matter. We'll take the first one later if we want, but let's take the solution e to the 3I x. And according to Euler, this is cosine 3x plus I sine 3x. Right? Euler? So notice there's no i's in the angles here for the sine and cosine. I guess that's it, huh? y2 is equal to cosine 3x plus I sine 3x. Wow, that was easy. Oh, wait, we still have a complex number here. I. Oh, wait, I is constant. Well, let's take a look at what happens to the second one. E to the negative 3I x equals cosine of negative 3I x plus I sine negative 3I x. Yeah, I don't think it matters. We're just going to multiply it all anyways. Oh, yeah, yeah. Thanks. You can do that. Cosine negative 3x. What do you know about the cosine function? It's the same. It's an odd function, they call it. So this is actually cosine 3x. I don't know about cancel. How do you know about sine? Sine is cosine is the even function. Sine is an odd function, which means you could take the negative out. Yeah, but so imagine doing this: C1 times Y1 plus C2 times Y2, right? Because this is what we want our solutions to look like. So if you add them together, we're going to have C1 times this, C2 times this, and C1 times this times C2 times this. Should we do it? Let's do it. C1 Y1 plus C2 Y2 is equal to C1, that's a cosine 3x plus I sine 3x plus C2 cosine 3x plus or minus I sine 3x. What do we have? C1 cosine 3x plus C2 cosine 3x. Oh, wait, we could just factor out a cosine 3x, right? Wait, is that what we factor out? C1 plus C2 cosine 3x. And then for the sine, we have C1I minus C2I sine 3x. That, did I do that right? This is an easier type of algebra. I think I must have done it right. Yeah. Yeah. What? So C1 is a constant, C2 is a constant, so C1 plus C2 is a constant. I is a constant. C1I is a constant. C2I is a constant. They're all just constants. It's still a constant. Yes, we disregard this. Like, wait. Yeah. So I think the thing to say about that is that it can be complex numbers, but when you do the IDP, initial value problem, when you do the initial value problem and you use initial conditions, then you're always going to come out with real numbers if your initial conditions are real. Okay. So what does that mean? That means really our fundamental solution set, we're looking for two linearly independent solutions. Y1, we didn't even address this, but Y1, where's Y1? Y1 is here and Y2 is here. Together, they are not linearly independent, right? Together, they're linearly dependent. But portions of their solutions can be taken out and then can be recombined linear combination. You can have a linear combination of those two functions that are actually linearly independent. So cosine 3x and sine 3x are linearly independent, so they can serve as our fundamental solutions. Yeah. The original y1 these two functions here are not linearly independent, because you can try to write one as a multiple of the other or something like that. Can you? And you can put it in the Wronskian and find out. So if we just take pieces of the solutions that we got from there, they can serve, for us, they can serve as the fundamental solutions for our differential equations. You smiled. You were looking all mad and confused and stuff. I wanted to get that. You don't smile. Ellen, uh, could be. This is, well, it depends on, yeah, it depends on, yeah, our B is equal to 0 in this case. Again, that the spring idea, we'll talk about the spring idea next time after we've gotten through some of this. But in this case, B over here is the damping, it helps the damping constant, and it's not, it's 0, so there's no damping at all in this particular problem. Some of those could have been, yeah. Yeah.
So put in the run skin, and we'll see if it's linearly independent or not. But were it not, or were it linearly independent regardless, we could just leave the solution as that, right?
We could. I think that's a more complicated way of looking at it. And it is also, we are still here in the complex world. And so we want to take that back to the real world. And we do that by, we do that by just, if we take a look at linear combinations of them, we can simplify our fundamental functions to just sine and cosine separately, instead of a linear combination of sines and cosines. Well, no, this is, I mean, this is easier now. Now we have simpler functions to deal with instead of simplifying. Yeah, it's like simplifying your solutions. And the deal is that it's always going to happen this way if you have complex conjugates. So the idea is just to get used to having these as your fundamental solutions. We're going to be talking about worlds, going into other worlds towards the end of the semester. No, we're going to go into, it's called the Laplace world. Yeah, we're going to go into a different world to solve differential equations. So the thing is that there's the real world and there's these other worlds that help solve real life problems. So these problems come up in real life situations, but then it's hard for us to solve for these things in real life situations. So in this particular example, we have to go to the complex world to see what's over there and then bring it back to the real world and say, here, this is our solution in the real world. Yes. Green. Spring. Again, I'll bring the spring mechanism here. I was going to bring it when we start talking about the non-homogeneous stuff, but it's the whole idea here is a spring. So my task today was just to show you the 3 different cases, and then we'll talk about the applications next time. Okay. All right. So If you haven't already noticed, we always came up with the same type of equation. The equation that we came up with, where we solve for the m, looks just like the original differential equation, right? Except it didn't have a y prime, y double prime, and y. It had an m squared m and then just a constant. And so this is what we have. We start off by assuming that our solution is of the form y equals mx, or y equals e to the mx. And then we take our derivatives. This is a second order differential equation, so we're always going to be doing two derivatives. And then you're going to plug those derivatives in to your original differential equation and then try to solve for the m, and you're always going to come out with an equation that looks very similar to your original differential equation. Okay, this is called an auxiliary equation, or the auxiliary equation. And so your auxiliary equation is a simple polynomial, in this case a second degree polynomial. And the solution to this will be the coefficient of the x in the exponential function. So now that you have this quadratic equation, we can explore the three different cases. First case is that we have two distinct real roots, and the two distinct real roots, we'll call it m1 and m2, and then your solutions are just e to the m1x and e to the m2x, and then you're done. Okay? Next case, you have one real root. Technically, it's one root with multiplicity 2. And so in that case, your first solution is e to the m1x, but then by the reduction of order process, we can find out, and it's going to work the same way every time, we can find that this is just going to, the second linearly independent solution will just be an x times e to the mx. And the third case, when you get complex conjugates for your roots, your complex conjugates would be in the form alpha plus or minus beta times I. And so in our particular case, our alpha was equal to 0, so we didn't have to worry about this. But in cases where alpha does not equal to 0, you have a real part in your complex conjugate, then you just have to keep track of where that's going to go. So your solution is e to the alpha x times e to the beta ix. And the beta ix, according to Euler's formula, can spread out to be a cosine beta x plus or minus I sine beta x. And so you pull out your fundamental functions that are linearly independent, and that would be e to the alpha x times cosine beta x, and then e to the alpha x times sine beta x. Okay? Didn't write the solution. Guess it didn't fit on one page. What's this? Oh, I think I was falling asleep and then just kind of leaned on the keyboard. All right. So I guess if I wanted to add this last thing over here, then your general solution is going to be y equals to C1 times that plus C2 times that. Okay. Yes. That comes from your solution to your complex conjugate roots, where our solution m was equal to plus or minus 3i. That's because this is equal to 0, and e to the 0 is just 1. It's not going to happen. So had our solution been 1 plus or minus 2i, then you're going to have an e to the x come out, and then cosine 2x and e to the x sine 2x. Okay. How is it? It's going to take some practice. So I was going to have you guys try for the next 10 minutes or so. Pick a problem. Okay, so that's to the 5th power. Let's just pick 1 through 14. Too nice. Let's see. No, I don't know. Let's try number 13. Why don't you guys spend 5 minutes trying to figure out number 13? Sorry, I'll put it up in a minute. So if you feel comfortable enough, you can jump to the step where you go immediately into the auxiliary equation. So you can bypass that e to the mx business. Just go straight to the auxiliary equation and then try to figure out what kind of form your solution is going to look like. So if you didn't already see it, this is an example where we would have complex conjugates, and then we actually have a real part that's not equal to 0. So we'll do something with that as well. And keep in mind that your answer, the two solutions, the two fundamental solutions are going to be the exponential function raised to the real part of your complex conjugate, and then the trig functions will have the complex part of your complex conjugate. Okay, so the i's will go away, the pluses and minuses will go away. You just focused on those two real and imaginary parts. All right, let's do this problem. Well, I'm going to do it. And I can jump directly to the auxiliary equation because I can kind of see it here already. So it'll be 3m squared plus 2m plus 1 is equal to 0. And then go to my quadratic formula. So it's not easily factorable, so I'm just going to go to the quadratic equation. So quadratic formula. So negative 2 plus or minus the square root of 2 squared minus 4ac divided by 2a. And then if you could just work this out a little bit, negative 2 plus or minus the square root of minus 8 inside of the square root. Then you can factor out a 2 from the 8, or factor out a 2 from a 4 from the 8, whatever. Minus 2 plus or minus 2 root 2i over 6, so that you can simplify this just a tad. Um, and if you want to match this up with the formula in the previous page, we have the real part is equal to negative 1/3 and the imaginary part is equal to negative or root 2 over 3. So the negative for the alpha is important. The plus or minus for the beta is not. So keep that in mind. And then if you want to just jump straight down to the formula, your y1 is going to be e to the negative 1/3 x times cosine root 2 over 3x. And then your y2 is going to be e to the negative 1/3 x times sine root 2 over 3x. And then you put this as a linear combination. And so there's a lot of stuff in the middle that's more theoretical than practical for us. And so in terms of just getting the solution, you can just jump straight down to what I'm doing here. But in terms of a theory type of a question, you might want to know what's happening in the middle. So y equals c1 e to the minus 1/3 x cosine root 2 over 3x plus c2 e to the negative 1/3 x sine root 2 over 3x. So some people like to actually factor out the e to the negative 1/3 x and then have the rest, the sine and cosine in parentheses. So that could work if you want, but then you still need to remember to keep the constants c1 and c2 where they are. Okay? So is that doable now? Yeah. Well, I think you do a couple of them by filling in all these steps here, steps. So if you want to follow through our case 3 example over here, the step-by-step example, go ahead and follow through that. But the bottom line is that in the summary, the bottom line is that when you have those complex conjugates, you have e to the something power times the combination of sine and cosine. And that's really the most important part of this. Okay? And we're going to deal with a lot of these types of questions. So you have to be ready to be able to handle it. All right. Hey, it's like we got 4 minutes left. Whatever. I'm done.